Good morning, everyone. So welcome for the morning session, and it's a great pleasure for me to introduce Klaus Mølmer. Quantum trajectories, what can we learn with a monitored quantum system? Lecture number 3.
Yes. Thank you very much. Welcome to the last lecture in my series of lectures here. I've started every lecture with this picture of the Niels Bohr Institute in Copenhagen, founded in 1920. I'll just tell you a little bit more about this building. We're actually standing at the stairs into another building of the Bohr Institute where Niels Bohr was living himself. So his private home was in the institute until he moved to the big villa of the founder of the Carlsberg breweries, which was donated to a prominent scientist in Denmark. So Bohr lived there for 30 years, and then other prominent scientists have been living there. Behind the window you see right here, George de Hevesy discovered or researched in nuclear tracers for biology studies and physiology studies and got the Nobel Prize for that. On the second floor, but facing the other side, was Werner Heisenberg's office. So he was a postdoc, as you would call it today, with Niels Bohr for many years. Behind those windows, Lise Meitner was doing nuclear fission experiments. I mean, she came to Denmark and later to Sweden. And there was actually 35 Nobel laureates collected in the Bohr Institute in the 20s and 30s. They didn't get the Nobel Prize when they were at the Bohr Institute. Only 4 scientists did that. But Bohr, when he was given the possibility to actually have his own institute, he insisted that it should be in a progressive, modern way. He had been in England with Rutherford, but he didn't like the hierarchy. He wanted to build an international institute, and everybody should have a right to talk to the professors and bring up their ideas. So there was a huge number of very young scientists who were doing everything they wanted to do themselves. Very few published with Bohr as a co-author, but of course they all discussed with him. So, you know, Heisenberg's papers are without Bohr as a co-author. Lev Landau was there, and there was a whole bunch of excellent young scientists in the early 20s. It was actually also after World War I, one of the few places in Europe where German scientists were invited. So there was an embargo on German scientists, and the Solvay conference in 1927 was the first one that Bohr and Einstein attended, because they had declined invitations until German scientists would be invited also to the Solvay conferences. So Bohr was a very progressive and modern thinking person, which is not what the first thing you think when you see the pictures of him and you hear him argue against Einstein, but he was actually very, very special in his relationship to young researchers. Well, anyway, I'll now talk about quantum trajectories. What can we learn with a monitored quantum system? And what I'm talking about is using quantum systems for sensing of classical properties typically, but of course that's what we do all the time, and that's one of the pillars in the various flagships for quantum technologies around the world. Quantum sensors may outperform classical sensors using entanglement and superposition and genuine quantum features. Of course, we already have lots of quantum sensors if you call an atom a quantum system, and they are. So we are of course using microscopic properties of matter a lot for sensing, but the new flavor, the second quantum revolution sensors, are the ones where we are engineering particular properties, maybe the crazy properties of quantum mechanics a little bit more. So why measure with quantum systems? Well, I mean, sometimes we really don't have a choice. If you want to measure something at the scale of few angstroms, you're not going to come in with a big macroscopic probe, but you can actually come in with a little spin. For example, an NV center spin in a diamond, and if it's located just a few nanometers below the surface, it's sensitive to the magnetic field caused by the spins of, for example, a molecule like this one sitting on the surface. So you can actually map out geometric structures, and you can learn about the presence of which atoms or nuclei are in the environment of a single spin. And then, of course, if you want to analyze the experiments on that one, you have to do the Schrödinger equation dynamics, or actually the quantum trajectory dynamics for this little spin system here, because that's doing things with it, measuring on it, and then from that trajectory dynamics, we're going to learn the properties we're interested in. This is another example where you imagine small gas cells in small glass containers mounted above the chest of a person. And they will be sensitive to magnetic fields. We have the same effect acting on the atoms. And if you probe them optically, then you can see what are the magnetic fields at the different locations of these small gas containers. And if there's a person lying here with an active heart, which we hope, then of course there will be electric currents in the nerve signals inside the heart. And these will lead to magnetic fields, and you can diagnose properties of the heart. They're particularly, at least in Denmark, in some of the hospitals, looking at unborn children's heart diagnostics. So this is not above the chest, but above the stomach of the mother, of course, that you can do this. And there are already little helmets with small gas cells inside of them, so you can actually trace nuclear signals. And you can do that now on children while they're playing, instead of sticking their head into one of these old machines where you could do that in the past. A ton machine that no child can carry that around, of course. There are optomechanical devices who can measure many, many things, but one thing is, of course, forces and accelerations. Atomic clocks and inertial sensors are also possible with atoms. Gravitational waves, probably the biggest, most impressive, and in my opinion, probably the only real quantum sensor using quantum physical effects today, measuring gravitational waves. And there are also searches for dark matter using some of the systems we know in quantum computing. There's a very long list, and there's a very good reason to develop theory for sensing with quantum systems. So what are the issues with quantum sensing? There's two very nice, now about 20 years old papers, but they're still very nice papers by Giovannetti, Lloyd, and Marcone, Quantum Metrology, a fifth letter, and this Science article, Quantum Enhanced Measurements, where they discuss a lot of the issues with sensing, also much more than I'm discussing today, because this is the Trajectory conference, so I'll be very much concerned with measurements over time, but they are discussing many things here. So the scenario is that you have a system which is subject to a perturbation of some sort, field, force, acceleration, and therefore the state of the system changes, and the measurement on that state will reveal the change of the state, hopefully, and hence also the strength of this perturbation. That's really what we are aiming at. What are the limits to that? Are the limits set by the uncertainty you have in quantum mechanics? Of course, this is a little bit the same. Are the limits set by Born's rule and the fact that you always get random outcomes when you do measurements? What are these limits? Are there limits set by measurement back action? The fact that when you measure on the system, the state changes, so your next measurement will not be on the same system. Again, it will be on a modified state of the system. And there is definitely effects of that, and as I'll show you, there's actually very positive effects of measurement back action in sensing. Measurements over time is one scenario that I will talk about. There's also another very, very common scenario. Almost all articles about quantum sensors will be talking about preparing a very good initial state for the system, one who is particularly sensitive to the perturbation, let it evolve, and then measure the final state. So you can imagine that squeeze states of some kind would be very good at measuring a displacement of an object, for example. So this is not measurement over time. That's what we call prepare, evolve, measure time strategies. And I will not talk about them, but actually only well, I mentioned a few words about them, but then I'll go on to the trajectory versions. So before I get started, also I would say there's kind of two kinds of sensing. I'll jump a little bit back and forth between them. I'm really interested in estimating an unknown parameter. I call that parameter theta in the rest of this talk. It could be sitting inside the Hamiltonian. It could also be sitting, sorry, this is a movie. I don't know why it does that. It could also sit in the damping terms. It could be the decay rate I want to estimate, but just for the sake of matter here, I put it in the Hamiltonian. So maybe you want to measure that. That could be the strength of a magnetic field in an atomic Hamiltonian. So that's the magnetometer. But you could also have what is referred to as hypothesis testing. Is the system subject to Hamiltonian H0 or H1? And of course, sensing could be a big hypothesis testing problem where you ask, is theta equal to theta 0, theta 1, theta 2, theta 3? So in some sense, there's a connection between those two scenarios. And here's a quantum state. It's actually a picture from a field physical article where they had made a collective spin state of many atoms in an ensemble. And this is a kind of collective Bloch sphere for that state. And they think this could be very sensitive to something. And here I subjected to a perturbation, so now it looks like that. That's actually real. The theory for a true dynamics of such a spin ensemble. Now that I can clearly see the difference between these two. And if theta had taken another value, I might also be able to see this little snake object look different. But that's not what we can do in the lab. In the lab, we have to do a measurement on this quantum state. So that means I could, for example, measure the vertical position, so to speak, of this quantum state. And if I do it many times, I'll get many outcomes of these measurements. And from those, I should then see if I can actually infer that value theta. Now, quantum mechanically, I would never be able to distinguish two states better than what is determined by their overlap. So if you have two states corresponding to the two hypotheses and they are parallel, then of course there's no way to distinguish these two states. And quantum mechanically, we actually have a deeper theory of quantum theory of measurement who says, how well can I distinguish between two states if they are not orthogonal, but actually have an angle between them. You can guess the right, which one is a good one, and there will be an error for that guess, which is directly given by this overlap. Now, what is the best measurement strategy to actually extract information from this? So that's a really good question. What should I measure to obtain classical data from which I could infer the value theta? And what is the error bar going to be? So to try to be a little bit quantitative, imagine you do a lot of measurements just of this vertical coordinate here, and then you form a histogram of the values you get. You get a single point on this axis every time, and here I have done a few hundred, and therefore I get this histogram. And it's based on this histogram, which you can imagine is related, of course, to the probability distribution of that variable already in that state, that I want to infer the parameter I'm interested in. Let me just make it a little bit easier. So I have a coin, and I don't know if it's heads or if it's fair coin. So I toss it a lot of times, and then I get n0 times heads, and I get 1 times tails, and I want to estimate what's the probability of heads and tails. And of course, your estimator would be, well, apparently, if I divide n1 by n0 plus n1, then I'm going to get the probability, and that with my parameter theta in this particular case. Right? But of course, you also have to admit, if I toss this coin only 10 times, I could have gotten many other things. I could have gotten 1 less or 1 more, and 1 less and 1 more here. So that will, of course, be the error bar in these numbers, which will translate directly into the error bar in my estimator of theta. So that's pretty straightforward. And the same thing is true up here. We can translate the expected fluctuations here, which might also be of a Poissonian character of all these numbers, into how well we can estimate or distinguish between different candidates up here. So let's just assume that this data is going to be compared to 2 different predictions by theory, this prediction for hypothesis 0 and this prediction for hypothesis 1. Then you're going to ask which one is the most likely one. So we'll come to how we find the most likely one, but also what is the error bar when we narrow in on a whole continuum of theta values that you want to estimate from this kind of data. And this is where we use the Fisher information, and I'm happy that Felix already introduced that in a previous talk. Of course, I'll tell you exactly what it is again. So the error bar you get from this kind of measurement is 1 over the square root of the Fisher information. And this is also called the Kramer-Rao bound, this limit to how much you can get out of the data. And here's the formula that was already presented in Felix's talk. So the likelihood here is the likelihood of the data you get conditioned on the right value of theta. So there's a probability distribution for your data to record look like this. And that depends on the theta. Otherwise, we wouldn't have any chance of guessing what theta is. The variation of this thing with theta is what is extracted by this second derivative that you see here. So this, what we're actually doing is that we are taking this dependence on the data, or the likelihood to obtain that data, the dependence on the parameter, and then you're weighing that with the probability to obtain that data. So this expression here is the average performance of your sensor, because it weighted with the probability to get a certain data set. And then what you are weighting, what you are averaging, is the sensitivity to the data. So this is the Fisher information associated with having this data record. And of course, the data record could be now any data record, and you can do many, many samples. Every sample will give you an estimator, and those estimators will fluctuate by this amount given by the Kramer-Rao bound. So if you're sensing with a small quantum system, then you can do these measurements many times. And if these are n independent measurements, then the error bar in the end will go as 1 over square root of n. And what the Fisher information tells you is what is the prefactor on this thing here. So that's of course nice. Now I'm interested in something else. I'm interested in probing over time. So my measurement signal or my data signal is not going to look like that. My signal is going to be a time-dependent signal that I'm obtaining. So here's my quantum system. It could be an atom or whatever. And then I could have maybe a laser probing this or some other probe mechanism that gives a signal to my detector sitting over here. So this is where the fluorescence photons were ending up in all the trajectory talks we had, and it's still photons ending up in this detector, but now they have interacted with an atom who is sensitive to an unknown magnetic field, and I want to estimate that magnetic field, or detuning, or something else. And my signal, and you have seen this graph all the time because I'm so pleased with it, so I just show it in every talk. This is the data record as function of time. So this is actually the thing from which I want to infer that parameter. So you see here there's a graph as function of something else, but it's this thing that I'm going to turn into my sensing capability. And what you would expect at least for if this signal is ergodic, that means that there's no particular time dependence in it. It looks more or less the same everywhere with fluctuations. You would expect that as a function of time, you would get an error bar that scales as 1 over square root of time. You could imagine you could cut it into segments of a certain length over which it's completely uncorrelated in the next interval and next interval and next interval. And the number of such elements would be proportional to time. And then it's like doing that number of independent measurements on the system. But how do we find this prefactor A? What is the Fisher information for this kind of sense? And there's a lot of people now actually just talking about some in the old my generation and before, looking at this in a quantum setting. Belavkin, clearly the first, without many of us noticing until much later, as Howard told us in his talk. Hideo Mabuchi, Howard, Mankei Zhang, Madeleine Guta, and the list is of course continuing. This is now a very strong field. These are names associated with my group, so these are some of the works I will show you today with students and postdocs. So when you look at a signal like this, the experimental procedure would often be to integrate the signal, to say, okay, then I get a better signal to noise by integrating over a very long time. And then you better hope that the thing you measure is in some sense dependent on the theta parameter in a good way. I mean, and that's of course very often the case. But there's more information to be picked up in the fact that this is a fluctuating signal. The reason is that the measurement you do at any moment in time causes back action on the probe. And that back action on the probe disturbs the probe. So instead of having a system which you could imagine would be treated like being in steady state all the time, you're actually perturbing the system away from steady state. You're quenching the system. And when you do that, you will be measuring the system's time evolution away from equilibrium back towards equilibrium. And that depends also on the parameters in the Hamiltonian and damping rates. So in fact, in quench dynamics, there might be more information about the dynamical parameters of the system, the Hamiltonian, than there is in the steady state value. And I'll give you some very strong examples of that. So there's actually a big advantage of the measurement back action. And that's a consequence of the randomness. So there's actually a big advantage of the randomness of outcomes in terms of precision, which is maybe a little bit funny. That's a little bit opposite in the prepare, evolve, measure strategy, where you like to have the fluctuations as small as possible, because that's the actual number you measure in the end. So I've also shown this picture before, where you have a quantum system living in the quantum world, which is not a real world, but we have quantum systems we describe by quantum formalism. We can change the dynamics of that system because we can shine laser light on them. We can have a Hamiltonian here, which is also containing unknown parameters, and then I get a signal out, which is my data record. And now today, I'm not going to talk about so much what the state does, but if you have a certain value of theta, you will also have a certain state. And that state is the function of theta, depends on theta. That means the probability to get the data you get out here depends on theta, right? Because that's the normal Born rule through the state's dependence on theta. So if you know the probability of having the data conditioned on theta, that's not what you want. You want to know what's the probability of theta conditioned on the data, because that's your estimator. So you have to invert that. But this inversion is exactly what Bayes' rule is about. Okay, and we say Bayes' rule all the time, but actually I like to derive Bayes' rule for you, so you can see exactly what is Bayes' rule. So Bayes' rule is due to Bayes, and what is written here is a probability for the joint probability for having both property A and B happening or being right. Okay, and you can write that as A has to be right, of course, and then B being right conditioned on A being right. But you can also write it that B has to be right and then A has to be right conditioned on B being right. So this is an identity that you can set up. Now, in this talk, B is going to be the unknown parameter and A is going to be my data. So you can ask, what's the probability? And this is not, we are not interested in this one. What's the probability to get the data and theta being right? So I'm actually going to remove that. And instead, I'm going to elaborate on the equality between those two things. So here you have the probability of the theta. Let's assume a uniform prior or any prior for this. This is the probability for theta to have some value. And before you do the experiment, that's a broad distribution. This is the probability to get the outcome conditioned on theta. So this we know from Born's rule, if I know the quantum state. Now I come to the left-hand side. This is the actual outcome. There's a probability for this to occur, but you don't care about it because it actually occurred. Right? So this is just something that happened to you. It's going to serve for normalization of the probability, if you like, in Bayes' rule. And this is what you want, because this is the probability of theta conditioned on the data. So here is a formula. The probability of the theta conditioned on the data is given by the prior probability times this thing. And that's base rule that I'm just quoting to you now. And proportionality because I just have to divide by normalization. So this is makes the trajectories immediately allow us to update probability distributions, of course. So then you update the data, then you go back, now you have a new P of B, and then you do it again, next measurement, next measurement, next measurement. So the quantum trajectory is iteratively going to update the probability of the theta. And the data record is now going to be the set of outcomes A1, A2, A3, A4, A5. So it's the whole data sequence that's going to be involved in making this distribution. So let me show you in a very simple example so you can see exactly how it works. Here's a spin which rotates with some frequency. And omega is going to be the unknown parameter here. But I know, of course, if I know omega, then I know the amplitude on spin up and spin down. If I measure the spin along the z-axis at time tau, then the probability to actually see spin up is going to be cosine squared omega tau. It may switch, and actually what is happening is at every measurement, there's going to be this probability that it will be found in the same state as before. So it can also be in the down state, and then it will rotate. The probability to be again in the down state next time is also this formula. So here's a simulated record, and you can see this is also showing the amplitude here, the probability going down, but then I measure it to be up randomly, up, and then down a few times, up, down, up. So this is a measurement sequence. During the talk yesterday by our chairman of this session, I was saying, wow, I never thought about the return time of this thing. That's going to be exactly this average of 1. But you can see that you return immediately here, but then you stay for, so this is maybe a long length n. And then you have of average length, the same length, you're going to stay away. And then you get exactly this magic integer return average time. But that's not what we're talking about now. I want to use now this measurement record to infer the value of omega. So don't look too much at these curves because they know the value of omega. Pretend you only get the clicks, but instead you have 3 candidate values. One which is omega 0 over 2, omega 0, and 3 omega over 2. Okay. This was actually done with omega 0, as you might guess. So they start out with having prior equal probabilities, and then because I don't see any change, even you would intuitively say that's more compatible with the lower frequency than with the higher frequency. So what is happening when you get you are still in the same state is that this orange curve is rising, confirming that it's more likely that you have a low frequency or no frequency at all driving the system. But then there is a click, and as soon as you get that click, you have to revise your view, right? Because now it's actually more likely that it's one of those two guys. So the blue one goes down because that's the highest frequency, most incompatible with the data, least compatible with this data, but it now rises. And the renormalized distribution will now go on again. Again, there's a duration with no clicks, and again, the orange one will rise, the blue one will shrink, the black one sits somewhere in the middle. And after this whole record, the black one has converged almost all the way up to 1. So it's a very simple example of this iterative application of Born's rule. You can ask too few and too many questions. So if you ask too often, then you will run into a Zeno regime where you don't learn very much because there are going to be very few of these clicks. They are hindered by the fact that you measure very often. If you measure very rarely, there can be an aliasing problem because you can make whole multiples of 2 pi rotations between the clicks. So this is what you see here. This is the probability distribution in a color plot where I have discretized the omega axis from 0 to 4, and the real value is actually 1. And you can see that you are narrowing in around the true one, but here you're narrowing in both around the true one and some wrong ones. And if you pick sort of the right one in between, you will only have 1 coming out with some error bars. So this is completely classical analysis, but there's a funny gymnastics around the Zeno effect here. So you can probe too hard, and then you don't learn much. Now let's go to a quantum system, a quantum trajectory, and we can take my favorite trajectory as the first one, the fluorescent from a 2-level atom, which we can simulate by Monte Carlo. And now, of course, I'm going to use the quantum jump clicks to estimate something. And what I want to estimate is I'm going to have an atom which is driven by a laser. So there's a Rabi frequency going up and down here. And that's the Rabi frequency I want to estimate. So the strength of the laser, or the laser field amplitude. So these are the simulations I already showed you. This is the average, but we're not talking averages. We're talking about the click record here. Can I from that infer what is the Rabi frequency? So the 2-level system we are talking about has a master equation or a stochastic master equation. There's a drive, there's maybe a detuning. I put it to 0 just in my example here, and there's a decay rate gamma to go back to the ground state. And if I know that the clicks happened at certain moments in time, then for a given Rabi frequency, the evolution is going with that Rabi frequency up and down with the clicks happening at the experimentally observed times. So now I'm not simulating the clicks. Now I'm actually listening to my experimental colleagues who tells me when the clicks happened. And then I'm going to say, well, that means I'm interrupted like that. And this could be true with this Rabi frequency, but it could also be true with the lower Rabi frequency. At exactly the same instance, the oscillation of the trajectory would then look like this. So actually the clicks happening in this figure here are at the same times as the click happening in that one. Or at a higher frequency, Rabi frequency, it would look like this. And it's hard to see, but there are jumps happening also here at exactly the same time. And now I'm going to align them under each other. So the vertical lines show where the clicks are happening. And I put these little stars so you can see that, okay, this is where the atom was. This is how excited it was when the click actually happened. And the rationale here is that, yes, there was a click happening here. Now, the atom was so excited. So the probability for that a click occur is actually proportional to how high is the star above 0, because that's the excited state population. And the decay rate goes as gamma times the excited state population. So this click and this click and this click occurred with probabilities which are the heights above which these stars are above the surface. And down here, these are the heights. And down here, these are the heights. So you can see that there are some here which are very small. This click here is almost impossible to expect to happen because this atom is in the ground state when the experimentalists saw the click, under the hypothesis that this was the Rabi frequency. So this is actually a data point who by Bayes' rule will rule out this with a very high probability to be the true one. And if you just have to multiply actually these heights to get the Bayes' rule update of the prior probabilities for those three. So this is the winner. This is the one who has the highest probability, and it's actually a very effective elimination. So let me show a real simulation instead of just my own little hand drawing. So here's a two-level system, and what I'm showing here is driven off resonance, and there's damped Rabi oscillations going on between the clicks, and all the clicks you can also see these are these market points where you return to this full contrast oscillations. There's about 30 clicks happening in this little figure. Now, just to compare with a normal estimation of such a parameter, the system in steady state would have an average population in the excited state, which is a function of the Rabi frequency. First, it grows with the intensity of the field, but then it's saturated 1/2 in a two-level system. So it actually means that if I just know the number of clicks to be, say, 20, then plus minus square root of 20, which would be an estimate of the natural fluctuations, would be an error bar this high. And that would mean I wouldn't be able to distinguish any of these Rabi frequencies from each other if I just told you I had 20 clicks. Right? You know, you go to your lab instructor in your lab course and you say, I think the Rabi frequency is 2.897 because I measured 20 clicks. And he would say, well, put the error bar on that, and then you would discover the error bar is actually pretty high because you multiply by plus minus, or you the equivalent of plus minus the square root of the signal. But we are not going to use the total number of clicks. We are going to use where the clicks actually happened. And this is similar to the figure I showed you before. I make a discretization here between 1 and 7, and then I see what is the probability for the Rabi frequency to be at a certain value. And you can see it almost instantly collapses. After 5, 10, 12 clicks, you already have a very small error bar in this estimation. And the reason is exactly the mechanism I told you, because every click is going to be followed by these Rabi oscillations. There's no saturation in the dynamics in the trajectories, so they actually oscillate, and therefore you have this clock running, which is going up and down at frequency omega, and the next click cannot happen when the atom is in the ground state. It can preferably happen when the atom is excited. So you are as sensitive to the Rabi frequency at high frequencies as you are at low Rabi frequencies. Here we're doing the same thing with Homodyne sensing. And that's a little bit more difficult to understand because the Homodyne signal is just very, very noisy. And there's correlations in that signal because there is back action happening on the system. There's a quantum trajectory who says every time you measure a little noisy thing, then for the future of that system, it will have, of course, experienced that little stochastic change in the state according to a stochastic master equation. But when you do this kind of, again, color plot, you can see that after some time, you have squeezed in, and you will know again here also what is the Rabi frequency driving this atom, staying with that simple example. Here I'm doing Homodyne detection, And the system is Rabi oscillating in the Bloch sphere in the XZ plane. So I'm measuring the X coordinate when I'm doing this Homodyne detection. So what you're seeing is that when you are running around with your Bloch vector with frequency omega, your Homodyne signal should oscillate back and forth because you're measuring the X component of the Bloch vector. And that's what makes it possible. You are sitting at y equal to 0 in that plane, so you shouldn't be able to see anything if you do the Homodyne detection of the y quadrature. But in fact, you do see something. And the reason is that when you do the y Homodyne measurement, you get random kicks out of that XZ plane, and you get finite values of y because you measure y. So the dynamics actually becomes a little bit more 3D of your Bloch vector. But it's still not ideal. As you can see, you have a big error bar down here compared to what you see up there. So I like to not only show you how we simulate things, but I also like to do, as I did in this first illustration, how well are we doing on average? Because every time you do a single trajectory, you will have a random record, and then you will have an estimator based on the random record. But what if you did another experiment? Then you would have another random record, and then you would also have another estimator. So if you want to know how good is this method, you have to know how much are these estimates actually fluctuating from shot to shot, because the true value can, of course, be any of them, because they have done these measurements with the same true values. And that's where this fish information comes in. This is where we get this averaging over all the possible outcomes of the experiment. So now it's going to be averaging over all possible trajectories. So that makes it a little bit more complicated. But it's the same formula as before, but now you have to think of this data being the entire data record. Okay? And there's a probability to get that data record. Right? And then there's going to be a dependence on that probability on the theta parameter. And that's what Felix was also discussing in his talk with first a very simple Markov model, and then it was growing in complexity. So that's something we started with students on Gammelmark. And so just reminding you again, the data record could be a Homodyne current. It could be the jump, the clicks happening at these particular times. It could also be, of course, a general measurement, so it doesn't even have to be continuous monitoring. If you have a system who evolves and you go in at certain times and performs discrete sets of measurements, they will generally be described by the outcomes of a POVM type measurement you do many times. And we make a theory which is the general theory, namely for the one for POVMs, but then with special cases to Homodyne and jump detection. So, and the general numerical method, I say a little bit about how it works, but so we actually sample the probability for the data record by the trajectories themselves. So you do many simulations, and then of course they will get single things, and what they get is something you just got, but you don't have to assign a probability to it because that's the sampling that is taking care of that. But you want to know this derivative, and that's more complicated. Then either you would assume theta and the theta value very close, and then you would do those two trajectories and do a numerical differentiation. But it's actually a little bit more precise, a lot more precise, a lot more robust to evolve from the dynamics. I call it Hellman-Feynman. That's not exactly true, but the way that properties depend on a parameter in the equations of motion can to first order be found just by looking at what are the derivatives in the equations of motion. So let me be a little bit more concrete on that on the next slide. Technically, we find that the classical information for counting and for Homodyne detection in the good direction is 4 times the total probing time divided by gamma. So you see, this is a time and this is a frequency. So this is a time squared. But that also means that 1 over the square root of that is going to be a frequency. So this is going to give us the uncertainty on the Rabi frequency. And it's independent of where you are with your omega. So this is a thing that has the same value for any value of omega. It's a very simple function. It's just this quantity here on resonance. So this record here is actually quite easy to calculate the classical fish information in an independent way, because every time there's a click, the system is reset in the ground state. And there's a probability distribution which is the same every time for how long you have to wait for the next click, because the atom is coming out of the ground state, Rabi oscillating. So this function that I draw here in red, that's the waiting time distribution, which we can calculate analytically. And if you do many, many experiments, then you can sample those waiting times, and they form this blue histogram, which is tracking this red curve. And what you really want to see is, if I change the Rabi frequency, then this red curve is going to be closer oscillations or more further away, or longer period of these oscillations. So you have to match the blue data to such a curve. And that's actually what we do. And then we can easily calculate this 4T over gamma dependence. The likelihood of this data record is just the product of the waiting time distributions for each interval, because that's the probability that the click came that much later. So analytically, when you take the logarithm of that and you take the derivative, you're going to get the logarithm of a product is, of course, just the sum of these terms. So you're going to get n terms, which are all about differentiating this one with respect to the Rabi frequency. And that's why it's so easy to do. Now, for Homodyne, it's actually a good deal harder, but we can calculate by the method I'll show you in a second that it's also 4t over gamma in this particular case. Maybe surprising because the back action is weak, but there's a lot of information in this record, not only from the previous measurement, but actually from any previous measurement, because the system is not reset. This is not a renewal process. It's just being gently pushed around, and every earlier push is in some sense still present in the system at later times, at least up to a few damping times of the dynamics of the system. We tried to analyze how much could we learn just from two-time correlations in this signal. So if I take the Homodyne record and I ask not for its mean value, but for its two-time correlations, there's a funny connection, because the two-time correlation function of the signal is the Fourier transform of the spectrum. And the spectrum, if you drive a two-level system, is going to show the so-called monotriplet. So it's going to have wings. And these wings are moving further and further apart the larger the omega. But they are equally distinguishable. And the position of these peaks is equally distinguishable for large omega as for small omega. So the two-time correlation function already tells us that we are going to have good sensitivity also for high omega. But when I calculate the Fisher information associated only with the two-time correlations, my ability to recognize the side peaks of the monotriplet, I get 8t over 27 gamma. Okay, that's not important what is the number, but it's actually much smaller than that. That's 4t over gamma. So there's more information in higher order correlations, which is of course no wonder. So we made some theory to calculate this quantity that you see right here. And this is what I already showed you, sometimes easy, but generally it's harder. And just to offer a glimpse into it, it's not because it's very difficult theory, but I just want to illustrate what one way to look at this. So you have your quantum system, and now I'm going to be a little bit quantum interaction-like. This is the system alone in the world. This is the field degree of freedom we are interacting with, who is in the vacuum state. And then there's an interaction between the system and the field. It's kind of input-output theory governed by this unitary dynamics, which is going to create or allow at least the possibility that there's some excitation going from the system into a one-photon state in the field. That's the spontaneous emission process. This is because I put the Fock basis of this field. I could also say that the system and the field became entangled using the X quadrature basis of the field. So that could be a continuous variable that you could have sitting out here. So the time evolution with the system in a short time window is establishing a connection with the output field, leaving it that short time window. And then, of course, it goes on for the next time window, next time window, next time window. And this is segments of the beam that is traveling towards you away from this particular system. And there's going to be a big quantum state, which, okay, and then what I didn't say here is that if I take a particular basis here and expand the state, then actually associated with a certain state of the field, there's going to be also a state of the system, and this U effectively becomes this omega operator acting on psi. That's the way we introduced its POVMs. So if you measure this M0, the back action of psi would be that omega operator. But it's nothing but a smart way to write the unitary on the product state turning into an expansion on this basis state. And now you have a classical data record. If you measure these quantities M0 up to n-1, and you have a state of the system, which is the quantum trajectory. Okay, so this is a quantum trajectory conditioned on that measurement record. But of course, if you don't measure anything, you're going to have a superposition of something very entangled, namely the system in this state and all the light segments traveling away being in those quantum states represented here. Now, for the classical Fisher information, we actually assume that we measured one of these sequences. So this is the trajectory, and the norm of that state is the probability for that trajectory to have occurred. Okay. So that means I already know the likelihood of that data record conditioned on theta, because that's exactly the norm of that state that you see right here. If you run the Monte Carlo wave function or the stochastic master equation in a form where you don't renormalize it, that's actually the norm of that thing, which is the likelihood. And this is not my discovery. This is in papers by Malbucci and Weisman and many others, of course, from the early days. realized. Now I need the derivative of that probability with respect to theta. And what I'm saying is that if you want to know the derivative of this state with respect to theta, it's like a perturbation theory. You want to modify the theta inside these omegas. And then to first order in perturbation theory, you can actually get an expansion for what is going to be that change in probability. And that is detailed in this particular paper here and was also discussed in Felix's talk. And if you want to average that norm, the derivative of that norm, well, then you can sample this many, many times, because then you will automatically encounter those quantities with a correct probability distribution. So we are doing this by simulation, but we're not doing derivatives on the simulated data. It's not very complicated. If you want to know the fish information with 10% error, you need 100 trajectories. I mean, just to give a rough number. So you can get that fish information with adequate precision. Of course, I would have loved to have had a deterministic theory, but this is the average of something which is nonlinear in the quantum state. I have the density matrix that takes the derivative squared. So I have a quantity that doesn't have a simple master equation governing its dynamics. At least I couldn't find one so far. So that was the classical fish information. Now I'll go to something that was really fun to work on. What is the most we can learn by any measurement? So you might not always be able to learn the same from Homodyne detection as from counting. And we also saw that the X Homodyne was better than the Y Homodyne if I wanted to measure the Rabi drive on a system. So of course, as a practical question, you would like, what should I measure to learn the best? And the question is a little bit complicated here, because it's a combination of what you measure is also causing the kind of back action on the system. And then the later measurements will, of course, be something which should not only be the sensitivity to theta, but also the sensitivity to these back action steps, which is where a lot of information is going to sit. But in the very abstract, let's assume we measure nothing. Because if I measure nothing, I'm going to have a big quantum state. That was actually the big quantum state I also had on the board before, but I can just show it here. That's the one represented by this sum of all possible records, and these being still quantum states of the field. So here in a picture, I have my quantum system, and then I have a big quantized field, and after 1 second, that field is 300,000 kilometers long, or 300 million kilometers long. It's all the way to the moon. And in all that light, there's going to be 10 to the 12 photons, 10 to the 18 photons. And all these photons are, of course, deeply correlated quantum mechanically. There may be anti-bunching. There's a lot of features in that state. So that quantum state, if I know that quantum state as a function of theta 1, and I know it for theta 2, then the distinguishability between those two is governed by the overlap between those two. Because that's my ability to see the difference between that state and that state. That's a question, how orthogonal are those two states with each other? So here are the states again. So I actually would like to calculate that overlap, but of course I cannot calculate the state. There's a reason we do reduced density matrices. That's because that Hilbert space is ridiculous, and nobody can calculate that state. But it turns out it's very easy to calculate that overlap. It's very easy to calculate that overlap. So that's nice. So here's the picture again. Let's assume just two hypotheses here, H0 and H1, and you get wildly different states of the field. In one case, the other case, and I'm not detecting it, but I'm, of course, going to at some point maybe do some measurements, and the question is, what should I then do? But before I do that, I just ask, how well could I even dream about distinguishing those two situations? So can I distinguish the two global quantum states here? Let me illustrate them as just this is one state and this is the other state. So they are state vectors, of course, in a huge space, but they will span their own little two-dimensional subspace. And it's really the angle between those two. So if you have a spin qubit or you have any other quantity and somebody asks you, are you in this state or that state? You can ask yourself, well, I could of course ask, am I in the blue state? And then you will with certainty get a yes if you are in the blue state, but the red state has also a probability to say yes to that question, which is just the overlap. The best measurement strategy is actually to pick angles 90 degrees apart, as close to the red one and as close to the blue one, and then assign that outcome to the blue one and that one to the red one. If you do that, there will still be a measurement error, but you have minimized the measurement error. So that overlap completely governs what is going to be the measurement error in hypothesis testing. So if I can make that overlap between those two states, I know how well I could ever hope to distinguish those two states. So the minimum error depends on this quantity. And now I'll show you a trick to make it easy to calculate. So of course, nobody can calculate the state, but we do it the quantum information way. So let's assume, this is not for the lab, this is not for the physics, this is just for the theorist. Assume you have an ancillar qubit in a superposition of 0 and 1. And that Hamiltonian is controlled by the qubit. So if you are in 0, you are subject to H0 down here. And if you are in 1, you're subject to H1 down here. That means that the system will evolve into the entangled state of the ancilla and the system 0 psi 0 and 1 psi 1. And now there's a nice little thing you can see here, because if psi 0 and psi 1 would be the same, then this would be a factorized state, and your ancillar qubit would still be in 0 plus 1. But because of the difference between those two states, you have decohered the qubit. Right? It's no longer a good superposition state of the qubit if those two states of the qubit environment are not the same. So what is the overlap of those two is actually the amount of decoherence of the qubit. Okay? And that means that this psi 0, psi 1 overlap is nothing but the mean value of the Pauli operator, transition operator between 0 and 1. Okay, does that help us? Yeah, it helps us hugely, because the small system composed of the probe system and the qubit, they solve a Lindblad master equation, because this is the signal which is leaving into this big reservoir. So I have that master equation for that joint system. So instead of having my small system, I have another small system, slightly bigger, namely tensor product of a two-level system and my small probe system. Okay. So I have a master equation for that thing. And this expectation value you see here, that's going to be the Lindblad master equation expectation value of that qubit observed. So I just have to solve a small master equation. Here it is. So for this system, you will have a tensor product. So it's a block matrix where you have the 0, 0 for the qubit element, but this is then the density matrix of the system down here associated with the 0, 0 component, 1, 1, 0, 1, and 1, 0 component. And it's actually that guy I don't want. The trace of this little block matrix here is going to give me the mean value of sigma minus operator. So trace rho 0, 1 is the overlap we are looking for. So I have to solve for the master equation for this object. And funnily enough, you don't actually have to solve for the other ones. There's a closed equation for just this beast, and here it is. It's the Lindblad master equation with an important exception. Every time I act on the left on the row, I act with the 0 hypothesis. And every time I act on the right, I act with the 1 hypothesis. So I call this the two-sided master equation. And if the hypothesis was associated with the jump operators, then every time a jump acts from the left, it's the 0 hypothesis, and every time from the right is the 1 hypothesis. These terms have two jump operators, but they're both on the left, so therefore you have this hypothesis, this hypothesis. This equation is not generally going to conserve the trace, because this is not a commutator. But of course, that's also what I don't want, because the trace is important here. It's the trace I'm looking for, because it's that trace who's going to give me the distinguishability of the state. So it's when this trace goes to 0 that the two states become perfectly indistinguishable, and this will happen with time. And there's no surprise, of course, with time you have the states emitted containing more and more differences with a function of time. But it's a very, very simple theory. It's super easy, of course. This is a deterministic, it's not even a stochastic master equation. So we solve this master equation for systems, sensors of even fairly big size. Of course, you can solve this master equation. And then you can learn how much you could have learned from this system. So this is the quantum Fisher information. Actually, I told you just to distinguish two hypotheses with this equation. But you can also take two hypotheses, theta 1, theta 2, take the derivative of this quantity with respect to theta 1 and theta 2, put them equal to a certain value theta, and then you get the quantum Fisher information for parameter sensing, for the error bar on theta estimation here. So it's yeah. Yes.
So, and it's not a commutator, but what do? You either apply one or the other?
Yes. When I solve the equation, I apply H0 on the left on the density matrix and H1 on the right. So in the same equation, both hypotheses are present, right? So you solve this equation with both H0 and H1. And this equation will give you a density matrix loss of norm. It will give you a trace of this crazy density matrix. It's not even a density matrix. It's not positive, definite either. But it's a matrix whose trace is actually going to be the same as the overlap between the big states, according to the argument I gave. So it's a simple mathematics. Of course, I could not have cooked that up without an explanation. But the explanation was this ancilla gymnastics I made before. So So this is accounting for the decoherence of an ancilla, which just happens to be the overlap I'm also interested in. And then I can put the two hypotheses infinitely close, and I can do the derivatives, and then I get this. And again, you can do from the master equation derivatives of the driving terms. So again, you can get an effective perturbation theory for this result, so you don't do any numerical derivatives here. So we have an effective way to do that. And if you do it for the two-level atom and the Rabi frequency, the quantum Fisher information is 4T over gamma. So all this light leaving your two-level atom on the way to the moon, you might just as well count it right away, because you get all the same information from counting that signal as you do from any advanced analysis of that big.
Just had one question in this context. This notion of quantum relative entropy, given two density matrices of two quantum states, one can define a quantum relative entropy, which is also, I think, closely related to this.
Yes, this is true. So in some sense, you can say that Fisher information here is a little bit like a quantum relative entropy between two pure states, and there's a generalization to also to mixed state. For mixed states, it's not clear how that connects to the sensing property. This argument I gave here really assumes pure state. It's actually a weakness of this argument, that this only works if you monitor, or imagine that you can monitor all the signal going out, because this is an overlap, and the distinguishability between two states is given by this overlap. Of course, there's also a distinguishability between two mixed states, but I don't think it will come out the same way with this formalism. But certainly, and there's a lot of interesting work on also relating the proofs that the quantum Fisher information is higher than the classical Fisher information, and that's probably also true for these mutual information quantities. So there's a relation, but I don't think I can say much clever about my ability to extract parameters in the mixed state case. But otherwise, thank you for the comment. I don't know if it was an online question or it was in the room. But
yes, from the online. Yeah.
Online, yeah, I heard your voice clearly. Thank you very much. So now let's come to some sensing of the time-dependent signals, right? So it could be fun to see. If the time-dependent signals is one where this parameter is not constant. Okay, so everything I told you was just estimating a constant. So how would we do if the quantity you try to estimate is changing all the time? It's actually not that easy, but when just qualitatively, we want to use Bayes' rule, but you also need a prior. And the prior is not just a prior distribution for this guy, it's a prior distribution for what is it going to be in the next time step. And that is going to be depending on what you think it is now. So there's going to be a distribution that is constantly being updated due to the fluctuations of the signal, and then it's also going to be updated due to the measurements you do. So it's a battle between two forces where the Bohr rule and the measurement will shrink the probability distribution for this unknown time-dependent variable now, and its own noise, its own devolution will cause to a spreading of it in every time step, because you don't know what it is in the next time step. And I can also only make this work if I have some knowledge about how it spreads. So there could be a number of noise models. You could assume that theta it's of course a classical variable, I just don't know what it is, but it could follow some stochastic process like the Ornstein-Uhlenbeck process, kind of damped Brownian motion type. It could be a Brownian motion noise. It could also be a hidden Markov model that just says that it has 50 different possible values and there are rates for jumping between them, and you know the rates, but of course you don't know where it is. So that stochastic process would also have a prior probability for where it is. And if you know that it is in one particular point, you also know what's the probability to find it in another point later. And you could also have a prior catalog of templates for what this theta could be. So it's a cosine function, or it's an x squared function, or it's something else. And then during your measurement, you're going to find out among those possibilities which one is the right one. So the examples I will show you will be with the Ornstein-Uhlenbeck noise, because they give nice, beautiful, ugly curves, and I want to estimate those beautiful, ugly curves. Without such a Bayes rule, it would be difficult to analyze the data, but I hope in the end I'll be able to show you how we get around also that problem. So the procedure, this is not necessary, but I find it very convenient to quantize the unknown. So this unknown theta has a probability distribution, which I can actually pretend to be the eigenvalues of a quantum operator, for which I am in a state which is purely diagonal. So there's a density matrix of theta, which is purely diagonal, with a probability distribution along that diagonal. So that's like a classical distribution. In this case, it is a classical distribution. It's just in my formalism handled as if it was a quantum degree of freedom. It's what we call a quantum non-demolition degree of freedom. So it's a degree of freedom who doesn't have any wave function dynamics. So it's not going to spread or solve a Schrödinger equation. So we have this distribution, and then associated to which, then I'm going to establish over time a correlated state where the system, my actual probe, is going to depend on theta. So the dependence of rho on theta is here captured in this state where theta is unknown and rho will have different values according to theta. Okay. This would also be true for a constant unknown theta. So everything I did before, I could simulate a number of these and update their probabilities, and that's actually exactly what happens in this density matrix. These guys get sub-matrices, a trace, which is the probability of theta, and as time evolves, these traces change, and that is the same as updating what we know about theta. Now our noise model is going to be some that kicks your distribution around between these theta guys, while the master equation is going to act on the density matrix part of this. So it's actually relatively straightforward to see how both the stochastic, or not even the stochastic master equation is going to give the conditional dynamics of each of these ones, depending on your measurement data, but also how the variations in theta is going to reshuffle all these populations among these different states. So it's a hybrid stochastic master equation. And a hybrid because it's quantum classical, but in fact, you can call it quantum if you want, because it looks just like a quantum master equation, where you have a quantum ancillary system with which you are becoming entangled over time. And the probability of theta is going to be the trace of this little submatrix theta here. So we have been doing that, and actually everything I showed you before with all these omegas could have been phrased like this, and then this color plots I showed you would be exactly a plot of how these traces would then shrink or point to one particular value. But now it's with the difference that I also add this possibilities for this theta to run around. So in this system, we have a spin sitting in a cavity, and we are probing it. It's a qubit in a cavity. We are probing it with a microwave field. It could also be a Benjamin's, a wonderful superconducting qubit sitting in here. And then I'm exposing this to a fluctuating magnetic field. The fluctuating magnetic field is fluctuating according to a Ornstein-Uhlenbeck random process. No, sorry, according to a hidden Markov model, but it looks like an Ornstein-Uhlenbeck process. So in this figure, the red curve is the true field. So there's some randomness going on. It goes up and down all the time right here. So it's just, that's what we simulated on our computer to start with. And then we did the measurement, Homodyne detection of this signal coming out of this qubit. And then this method, this approach here, leads to the probability distribution shown with the color. The bright color means high probability. The black color or blue color here means low probability. So you can see that this big yellow snake is following, of course, the red curve pretty well. You can say that the height or the thickness of this one is the uncertainty we have, or the probability that for the different values to be true. The most likely one is the green curve, and I apologize, it's not hard to see, but there is a green curve which is roughly following the red curve. If you look a little bit closer, I'm now walking closer, I can see that this green curve is typically trailing behind the red one, but that's of course what you expect, because you measure on the system, you accumulate data, and then you learn the values, but it's already too late. But of course the process has already changed again. So this is of course completely normal. Here's another example. This is an atomic gas cell where there's again a magnetic field. So this is one of these magnetic field sensors that we could imagine using. I use optical pumping, so the atom is well polarized all the time. And then when I'm probing, I can see how the magnetic field tries to drive it away from that optically pumped polarized state. And you measure that by measuring the phase shift of the light, or actually the Faraday rotation of the light in this device. But it's equivalent to Homodyne detection. And here is the same story again. So the green curve is the true randomly simulated Ornstein-Uhlenbeck process. So that's a noisy process. And the blue curve with the shading as an error bar is what our master equation gives us here. Here we are not solving it in a discrete representation of the density matrix. This system is well described by Gaussian states. So in fact here we just need to know the mean value and the variances of these Gaussians. So it's numerically very easy and mathematically very, very equivalent to something called Kalman filtering in classical signal processing. But you can see that it works, and again you see that we are lagging behind, of course, because we have to get the data before we can guess the value, and then the data change. So there's not much to do about that. So that's pretty nice. And of course, I've been talking about this retrodiction, and it's very tempting, or it's very natural with the quantum state we have here to do that, because I do have a time-evolving joint hybrid density matrix, and I can also do the joint hybrid effect matrix on this particular case. So up here we have, the same figure as before, based on the trace of this rho theta. But if you have this coming from both directions, you use all the data to infer the magnetic field at any point in time, you get this curve. Okay, so this is rho theta, e theta actually, that you have to multiply and do the trace. And now you're not trailing behind. Now the red curves and the green curves follow each other much more closely. Spikes are harder to get, but neither the past or the future can guess whether there's a spike or not in the middle. So this will be misrepresented. The error bar, the yellow stuff is much thinner here than it is up there. So the error bar is down due to this data processing. And we can do the same also in this other case, the Gaussian case, where this was what I showed you before, lagging a little bit behind. And then with Cheng, here we did the other method. And then you actually see that now we're not trailing behind anymore. And the orange thickness is also a smaller error bar than you see in this upper plot. In the Gaussian case, this was also known in the classical world. So the Kalman filters also come with a smoother, as it's called, which is a way to go backwards in time. And the mathematical formalism is just like that. So it's a part of the Kalman theory to actually go forward, backward. There's something called forward-backward equations, very, very tellingly. And of course, these have names also after the authors who made them. But there's a difference, of course, because the quantum state here, it is described by a Gaussian Wigner function. But it's unlike the classical case, there's quantum mechanics coming in. For example, Heisenberg uncertainty relation, which does not exist in the classical Kalman filter. So there are properties of these matrices that are fulfilled in the quantum case by the way we set up the equations. So this is at least also showing the strength. So this is really trajectory theory taken to the probably the extreme, because here we really use all the data available. And it's a base rule type update. So there's not more information in this data than we are using here. And before going on, this kind of curves were actually done in a theory much prior to my work. So this I have to say by Mankhej Zhang. So he had a very nice PRL and PRA articles in 2009 where he puts out this formalism. So that's the full retroduction also. He was not interested explicitly in any of these articles in a quantum state doing other things. He was interested in doing the sensing of such a signal. And in these papers, he's relating very well to the classical theory of sensing of signals. So you will find them maybe hard to read. I find them hard to read because there's a lot of knowledge about the classical estimation problem that he's using because it exists. Right? I mean, it's not an excuse for me not to make the effort to read that literature because I want to do the sensing. So there is an existing literature on classical sensing that is connected very well to this, both this one and to this, of course, retrodiction in Mankhej's papers. Now here's an experiment done by Yan-Hong Zhao at Shanghai. I already showed some of her results before. So when she's probing an atomic gas, she's squeezing the gas observable. So that's not a classical sensing. That's just ability to guess outcomes on the measurement on the system herself. And what we showed there was that when you measure, then you can actually better guess the in-between measurement data than later measurement data for reasons, right, that we talked about. And now we also want to do sensing of something. So now we apply a synthesized time-dependent magnetic field to the atoms to which we will be sensitive by our probing. So you can, out of a random number generator, you can produce an Ornstein-Uhlenbeck process, just like the analysis we did with Cheng, and then you can see if we can actually follow that Ornstein-Uhlenbeck process. So we did that, and I did the theory, and it was very good agreement, so the sensing is fine. The error bar around the true field was as expected from the theory. We put all the imperfections into the theory, of course. The damping is a stochastic master equation approach, so it better be good. But we also did another approach, and that was a deep neural network. So instead of doing any theory at all, we just trained a network by synthesizing lots of these signals. I mean, the magnetic field, driving the atoms, getting the measurement signal, and then we fed the measurement signals to a network, asked it to make a prediction for the magnetic field, and then we trained it until that prediction was a good one. So that was a prediction for the whole curve, the whole time dependence. And she trained 26 hours of data with this neural network, and then of course after that you start feeding it things where it has not seen the signal before, but we still know what it is, and then we can see how well are we actually tracking those signals. And that worked very well. So I mean, this is the Ornstein-Uhlenbeck process, and the real signal is the blue curve, and the The orange curve is the estimated value. So we are tracking very well what happens all over the place. And I have to tell you one thing, because we also did some theory modeling of this process. And the first time we did the theory modeling, I shouldn't have been surprised, but I was still surprised to see that the estimate is not very good in the beginning. Well, that's not surprising, because we need to accumulate some data first. But it was also not so good in the end. And why is that? Because we have accumulated all the data. Well, that's because at the end you need future data, because we learn something from the future data. And if there are no future data, you don't get that lesson. So the neural network, who does have no clue about master equations, it's just using the data, is also having an error bar which is increasing both in the beginning and the end, because it cannot learn so well in those phases here. So the network here has all the data to infer all the values, and therefore it is actually automatically trying to include the retrodiction aspect of it. Right? So that is what it does, and it also actually reaches, it saturates the Bayesian retrodiction extremely well. And of course, it has 4,000 free parameters, and it has spent 26 hours practicing, so it cannot really go wrong. But it's nice to have a benchmark with a real theory saying that this is how good this works for this particular case. And then, of course, we scrambled the dynamics. We did crazy things. We cut it into pieces and added random discrete jumps to the Ornstein-Uhlenbeck process at random times. And now I don't have a model for it anymore, and I cannot do that with trajectory theory. But the Bayesian retrodiction actually didn't care, because, of course, it's just training on the data. So you can, and I had many questions in my previous talks about non-Markovian dynamics, and we also simulated with students actually, what if there's a non-Markovian processing of the data? There's a beautiful paper by Howard, you referred to it, I think in your talk also, a late paper where you included dead time of detectors, dark noise, and things that are messy because you actually don't know what the system does, because maybe your electronic signals has a convolution over time also. But of course the neural network is just doing an empirical matching of the measurement data to what it's being told again and again and again is the true signal. And then when we finally give it one where it doesn't know the true signal, it can make a good guess. So I am telling my colleagues in sensing, Eugene Polsik in Copenhagen, that whether you like it or not, we are going to implement this with our sensors, because it's not very difficult, and it's going to take into account a lot of things which are very, very hard to model in the stochastic master equation. And then hopefully we will not be out of job. At least I would like to say then I can be the verification office in which I can then take the case where it could be solved just to see whether the neural network does reach what the theory can do. And then I will trust it and use it. So I have 12 minutes. I just skipped my conclusion slide. I have another conclusion slide. So I just want to say a little bit about LIGO. So I'm not a LIGO expert, but LIGO is a fantastic experiment. It's a huge interferometer where a gravitational wave will cause an interference signal. I mean, classically speaking, it will set this mirror and this mirror in motion, and the path length difference will make the Young interference pattern down here shake. And from that shaking, that optical signal, you would then like to infer what was that motion. So the mirrors are 40 kilogram heavy mirrors suspended like this, so they're not hit by too many other perturbations than the gravitational wave coming by, and now we're going to sense the motion of that mirror. Okay, on the LIGO homepage, they want to measure motion 10,000 times smaller than an atomic nucleus, okay, because that's what we expect to see. That's the smallest measurement ever attempted by science. It's ridiculously small, obviously, right? The mirror itself is a quantum object, so I'm going to talk about how this becomes trajectory theory, because you're actually probing the motion of this mirror. And let's just make an assessment of, do we need quantum physics to describe that mirror? So let me just ask, what is the ground state width of this motion of this mirror? So let's just do a little comparison with physical systems we know. The harmonic oscillator has a ground state width given by Planck's constant, the mass, and the frequency. And that formula you can use on almost any object. So if you know the mass and the frequencies, you can estimate the size. So take a hydrogen atom. Of course, that's not an oscillator. But the mass is the mass of the electron, the frequency is an optical frequency, and you get 10 minus 10 meters, and that's the size of the atom. You go into a nucleus, the mass of a proton, mega electron volt excitation energies, you get 10 minus 15 meters. That's good enough for me. If you take the LIGO mass, 40 kilogram frequency of 1 kilohertz, you get 10 minus 18 meters. So the ground state width of that mirror, that is actually an oscillator, is comparable to the displacement you want to measure. So we have to use quantum mechanics to analyze this experiment. The atomic mirror has a wave function, and there's a width to that wave function, which is broad. And when you measure, you're going to measure continuously because you don't know when the wave is going to come. So we're actually sitting probing the mirror position all the time with the good and bad consequences for our future measurements on that mirror. And they will be typically bad, actually. So let me just assume that I'm doing a very good measurement here of position x of the mirror to better than the ground state width of that mirror because I have to. And then there's a kind of collapse, a tightening of the wave function because now I know the wave function better than before. I know the position better than before. So that's cool, except we have something called Heisenberg's uncertainty relation. And if that wave function in x is so narrow, the wave function in momentum space is going to be much broader. The state has large momentum uncertainty. And of course, that will lead into the future position uncertainty because that will expand the wave function at a very high speed. So the very good measurement at an early time causes a very bad position measurement at a later time. And Schrödinger back in the 1920s actually wrote down a Heisenberg uncertainty relation for position measurements at 2 different times. And it grows with time, that uncertainty, right? Because there's this expansion going on due to the first good measurement. So it's a very interesting thing. And so he has this beautiful relation, and it exactly applies here. So it seems to be quite impossible to do position resolution better than the ground state width because you will kill the state later on. So there's a trick to that, and that's something called quantum back action-free measurements. Or Q&D measurements also in some sense. And they were invented for this purpose by Carl Caves and the heroes, actually, of gravity wave detection. But of course, they are in other branches of quantum physics and quantum measurements. The position of a particle is not a quantum non-demolition observable, because when you measure x, you change p, and that will change the future x. So you cannot just measure x and keep measuring x and get wiser and wiser about its value. Actually, the momentum of a free particle is a Q&D observable. Because while I measure momentum, I give position uncertainty. That will not change the momentum in the future if it's a free particle. So you can measure the momentum of a particle indefinitely well. That's a work by Braginski. Energy is a Q&D observable. So you can gradually collapse into an energy eigenstate. And of course, that's a stationary state. So you can keep measuring and it's still the same energy. A trick, well, before I actually tell you about the trick we will be talking about here, the trick employed by Eugene Polsek in Copenhagen is also a smart trick. The mirror is an oscillator. So if you measure position, it becomes momentum. But if you wait half a period, it comes back. So you have like a squeezing ellipse which is rotating. And since it is periodically returning, and you keep measuring x every time that it's getting, for example, standing vertically, you compress it, you let it rotate, you compress it, and then that way you will compress that squeezing ellipse in every measurement. Just be sure you don't measure p anytime, but you only measure the x on that rotating ellipse. So you do it in synchronously with the atoms. And actually, all Jan Hong's experiments that I described before are also done stroboscopically in the same way for the exact same reason. But there's another trick, which I think is just a fantastic trick. It's by Mankey, who I mentioned before, and Carl Caves, who was the hero of squeezed light in 1980 and wrote about using squeezing for LIGO. And now, 30 years later, he writes another fantastic paper to make LIGO even better. And that is something that these gentlemen call quantum free dynamics, that you can actually make quantum system have degrees of freedom that are purely classical. There's no back correction. You can measure them as good as you like. And the trick is to have 2 oscillators. And they call one the positive mass and the other the negative mass oscillator. And the one of them is the one who is actually exposed to the force you want to measure. The other one you keep in the back. So you're not going to have the gravity wave hit that one. I would say that Eugene Polsek has made a version of that experiment where he's measuring the motion of a membrane. So that's a mechanical oscillator. But the other oscillator, he actually uses an atomic ensemble, who also has an effective oscillator degree of freedom. So it doesn't have to be 2 copies of LIGO. It could be LIGO and atomic gas, who are 2 different oscillators. And what you're going to do is you're going to measure collective properties of these 2. Okay. When you measure those collective properties, you can actually measure the motion of this one indefinitely precise, both the momentum and position changes. In this case, of course, you want to put LIGO, and you maybe still want to put this atomic gas. There's a lot of technical issues because do you have the right bandwidth, the right frequency range of atomic frequencies and the LIGO thing, and will all of that work? Do we have the sensitivity all the way down to the very low frequencies of this mirror? Because we are really interested in the frequencies around 100 hertz, and in the future, 10 hertz, few hertz. because that's where a lot of astronomical information is going to sit. But I'll just present this mini analysis to you here. I have two oscillator systems. I'm going to probe them optically. They are, one of them isolated from the rest of the world, but the first oscillator is experiencing a force that will cause displacement of its position and displacement of its momentum coordinate. Okay, so there's going to be a displacement in both x and p. These are classical displacements, but of course, the object I'm displacing is a quantum object. If I have only one quantum object, I cannot measure both x and p precisely, right? It's an uncertainty relation. So therefore, there will be effectively an uncertainty in how well I can estimate those two displacement curves here. But now I have two of them. And because I have two of them, and one is of course going to be the LIGO mirror eventually. Oh, this was the wrong order. Anyway, this is what I already showed you. The displacements are classical amounts. So if I have two, I'm going to measure x1 plus x2, and that will tell me if there was any change in x1. And that's the one I interact with. There's not going to be any change in x2. So the change in the sum is going to be the change in one of them. And I'm also going to measure p1 minus p2, and that is going to tell me the change in p1. But the trick is these two guys commute. So they can actually be arbitrarily measured, precisely measured. And you can be in an eigenstate, that's the EPR state, which has small uncertainty in this guy and small uncertainty in that guy. And then in that way, you can actually measure the displacement on one of them. So you use an extra oscillator, and then you can do this precise measurement. I like to think of it as there's this fantastic story by Oscar Wilde called The Picture of Dorian Gray. So Dorian Gray is this handsome young man who lives a wild life, drinking and everything you do when you live a wild life, and he just still looks young and handsome. But he has a picture of himself in the attic in his house, and the picture looks more and more bad with time. So this is what is happening here, right? That you have this other degrees of freedom. And in this case, it's going to be the other oscillator who's going to be more and more messy and shabby, but you're getting the information from the first one. Or to be a little bit more precise, the x1 minus x2 and the p1 plus the p2 are the anti-squeeze components, but you're not using them for anything. So it doesn't matter that they're going to pick up all the back action and all the noise from the squeezing back action. It goes into other quadratures. x1 plus x2 causes anti-squeezing of p1 plus p2, but you measure this guy. So does it work? Well, yes, of course, it's already demonstrated in experiments. I just want to show our simulations with a student just 2 or 3 years ago. So here's the applied displacements on x and p, and this is the inferred displacement on x and p in this particular case. And of course, it's hard for you to judge whether this is going below some Heisenberg uncertainty relation, but it's much, much better than if you had a single oscillator and tried to do the same thing. Again, just to keep bragging about that idea, you can see that here there's a peak, and this guy is actually coming later. Of course it's coming later, because again, you're estimating something with a quantum system who has a finite relaxation time. So again, you could say, could we apply retrodiction to this data? And since it's become more or less my middle name at this conference also, of course I'll tell you that, yes, sure, we can apply retrodiction also to this data. So this is just one of them where we apply this known classical perturbation. That's the solid dark blue curve here. The normal one by this standard analysis is the dotted curve, which is following all the same trends, but as you see, always too late. And then we have this light green one, which is smoother, and at the same time also is tracking much better the true signal. So I mean, if I goes into this two oscillator regime, I'll call the guys and say, are you sure you're going to analyze by that? And of course they do, because they already analyze by much more advanced Bayesian methods when they analyze the LIGO signal. And they are not having an Ornstein-Uhlenbeck process, unfortunately. They're going to have something where the prior is not known, because you don't know what's going to happen tomorrow or 10 billion years ago, causing this spiraling event of two black holes. So what they have is instead a lot of templates for what they would look like, different cosmic scenarios. And then you can use Bayes' rule to infer which one of them did you actually see in the experiment. So pretty cool. And of course, the retrodiction, I think, will be particularly important because the high frequency signal at the end is very strong, very easy to recognize, and you have low noise in your detection at high frequencies, while the low frequency components are much more harder to discern. So you don't see them when they're coming, but when you actually at the end have the high frequency component, then it's easier to go back and look, which is done automatically by this method. But I mean, then of course there should be a lower and lower frequency component at earlier times, as you see in the LIGO signals. So now I come to the conclusion, 50 seconds, that's fantastic. So actually, this is just a mini summary. The state of a quantum system is conditioned on probing outcome, and In fact, there's a transient response to every measurement event, so you don't have steady state dependence on the parameters in the system when you're probing the system. And in metrology and hypothesis testing, this can be implemented in this Bayesian manner that I did, and we really benefit from the back action because the non-steady state dynamics is much more sensitive than the steady state expectation values. There's a golden standard for how well you could do, and that could be this quantum Fisher information. And for example, if there was extra loss, like the question I had about comparing density matrices, then this is going to shoot far higher than what you can actually achieve, because there's missing signal that you don't have. There's in Martin Plenio's group in Ulm, in Germany, there's a fantastic postdoc, Dayu Wang, and he has actually now ventured into this field. And I think he has a theory, so he can actually now generalize my quantum Fisher information to one who can take partial measurements into account. I look forward to see more about that. The Bayesian analysis of time-dependent signals only work if we have a prior probability. If you don't, then maybe you have to go to this machine learning, and then we can do that for the next 50 years. Thank you for your attention.
Thank you very much.
Very nice talk. It seems like in all of the measurement configurations you're considering, it's a very passive approach in that you're monitoring a system, you're taking the signal and so forth. But of course, there's lots of techniques where you're making adaptive measurements or you're adding controls, feedback. And so maybe you could comment on, are the limits the same, or they're better limits when you can consider?
So concerning the classical Fisher information, so of course the adaptive measurements have been very much pushed by Howard, and the classical Fisher information that we calculate, you can easily do the same if you have an adaptation strategy. So then we can actually also calculate the Fisher information. Of course, we can simulate it straightforwardly, and all the base rule updating will work with the adaptive strategy. The quantum Fisher information is a little bit more unclear because the adaptation can only be done if you do the measurement record, and therefore it has to have this extra stochastic element to it. So there I would be a little bit more in doubt. I mean, then I would have to say there's a quantum description of my adaptive mechanism. And then, of course, that could still be quantum. It's a little bit like Howard's fantastic quantum computer, AI with quantum properties, that maybe we could actually think about such a thing and then make my QFI argument work for such a machine. But I've not done it, but adaptation is of course something you do. You could do adaptation both in terms of measuring something else, because you think the signal is at another local oscillator phase, probably what you do in the lab already, but you could also apply control Hamiltonians to kick the system and to get some response out of that. The guidance to what is the good way to do, and just ask, the whole talk here didn't say what is a good measurement. I was just quantifying how good is a measurement. And when you talk about all this quantum measurement as being a part of the pillar, I'm completely independent of that. I mean, I'm just analyzing schemes by this method here. I'm not inventing schemes. Entanglement may play a role, but I was using it in the very end. Squeezing may play a role, but I was just objectively translating measurement records into something. All these ideas people have about using entanglement and error correction schemes and whatnot in more advanced schemes, they will then go into this adaptive scenario that you're asking.
Yeah, okay. So just two questions, Klaus. One quick question. So you had made this comment about how the prepare measure schemes, you don't get, you made a passing comment.
Well, sometimes you do. I mean, of course, they are the ones often in use, often because there's a funny thing you often hear people say. They say, this thing is hard because you have to do a full base analysis. And I always ask myself, what does a full base analysis mean? It actually just means a base analysis. But the word full is just to emphasize that it's a little bit hard because you have to include all the possibilities. So there's a big probability space. And of course, that is heavy. And so if you have, and also if there are unknowns, because there are things, there are dark counts and there are dead times and whatnot, then it gets really complicated. And I usually say to other people, and I'll tell it in front of Howard, that Howard wrote a fantastic paper showing how difficult it is. Scaring people away from ever trying to implement those theories because there are so many auxiliary variables that you have to describe in a probabilistic way.
Could I just, so my actual question was, these prepare and measure schemes, for instance,
there you have control more.
Monica Schaller-Smith and Vladan Vuletich's experiments, so on and so forth.
Yes.
They all go beyond standard quantum limit. And I believe your picture was a cartoon of that, right?
Yes. So
and so in some sense, I think part of the experimental strategy is to basically just say, I'll do the best I can with experimental resources. And I just want your reaction with respect to that. And my second question, Klaus, let me put it out. Could you please also comment on the measurement of the symmetric logarithmic derivative? In your opinion, what, you kind of briefly mentioned that it's very hard and so on and so forth, the thing that saturates the UFI.
Okay.
But if you had any more comments, I would like to.
Yeah, I'd love to do this. First, a comment on the standard quantum limit. So the standard quantum limit is that you have n independent measurements. Then the error bar will go as 1 over square root of n. And then, of course, if you have n atoms in an ensemble and you think they are independent of each other, then the precision score is 1 over the square root of the number of atoms. If that system contains entangled atoms, it's no longer independent measurement. And the most extreme state is the G8Z state, superposition of everybody in the ground state, everybody in the excited state. That actually has a resolution which is 1 over n. So that's going beyond standard quantum limit. And what Monica Schleyer-Smith and Anna Maria Ray and other groups have been doing, they have said, take your initial state, which is uninteresting. So that's a product state. Oh, that's very small. Uncorrelated state. Apply some scrambling Hamiltonian who really messes up the state. Now that sounds like a bad idea, because this very messed state, that is not going to be easy to find the observable who will see the sensitivity to this evolution under the unknown theta parameter, because the measurement is now on a really ugly big dragon of a quantum state. But if you can apply minus the Hamiltonian, then if theta was not there, you would go back to the initial state, where it is easy to measure where you are because you know what is that state. And if there's a small theta, this thing will bring you back to the vicinity of that state, and you will actually be very sensitive to what was happening here in between, much more than if you had applied the theta on that state. Because this big, I normally illustrate to students, moving a Gaussian a little bit to the right can be hard to measure, but moving a thing with these little spikes, if I move that by less than a spike length, I can of course see that. The measurement, however, is horrible, because it's a random measurement and the probability to get any of these signals is of course all very small. So this trick is fantastic. Okay, now we go to the standard quantum limit in time. So now, if you have a duration of time and it's equivalent to independent measurements, then you would also get some resource. But the resource count is different, right? It doesn't depend on the number of particles now. It depends on time as a resource.
Time as well.
Yes, that's what I find here, right? But you see, the going below the standard quantum limit, entangling the particles, can also be combined with a time-dependent sequence, because I can also get this scrambling going on as time goes on, and even the measurement back action contributes to this scrambling effect. It's less clear how it works. Peter Zoller and actually also Plenio and Wang, they have this concept that it could be a good idea to take a boring light pulse, send it through something very non-linear, so the light becomes very messy, like Monica Schleyer-Smith's very messy states in time, but this is in space. This is a time pulse with lots of internal complicated correlations. Anti-bunching, for example, if this was a two-level system. And then instead of detecting it here, you send it through another quantum system who might sort of unscramble some of this information. And this would be an encoder for the very sensitive time-dependent signal processing. And this would then be the decoder, a quantum object, before you send them. Okay. And this could also work continuous wave, right? So now I have a laser beam. I get a beam which is not just a boring laser beam, but a laser beam with rice in the soup, because there's a photonic structure which is very non-trivial. And if there's anything I want to sense here, then I would be very sensitive maybe in those rice in the soup. I just have to bring it back to something that's easy to measure, a mean amplitude, for example, or the noise on a mean amplitude. So I think the analogy to Monica's wonderful work with atomic ensembles can be carried into the time-dependent analysis. Sorry for the very long answer.
So, and very quick comment about SLD. What is your opinion about measurability of SLD?
Of measurement of a...
Or symmetric logarithmic derivative.
Oh yeah, so the formal structure, if I have this psi1, psi2 that I want to distinguish, there's a beautiful paper by Bernardin and Caves, who is not only telling what is the sensitivity given by this overlap, but they also tell you what you should measure. And that's related to this logarithmic derivative. So if you actually know the states, you also know which observable to measure. Okay, so if I give you psi 1, psi 2, which are very close, and I want you to tell which is the good one, there is an observable I have to measure related to this thing, right? And it can be identified. The problem is that our states, in my case, are this 300 million kilometers of light. And I don't know the states. I know their overlap, but I don't know the states. So I cannot extract the observable because I don't have the knowledge of the state, only of the overlap. So unfortunately, I cannot use that theory. Yeah, then I would just I would benchmark different classical measurement strategies and see how high they come towards the quantum fissure. But I don't know how to identify what is the best measurement to do.
Thank you. I have a very general question. Do you think that machine learning can distinguish between a quantum signal and coming from a quantum origin and a classical signal, or is there no way to do?
Yeah, I think it can. Yes. I think it can.
Without prior knowledge, I mean, is there no? I mean, for example, okay. So you think you can? So let's go back to the case.
Okay, I have to be careful because it's not like a Bell theorem, right? Now we have an AI and it says this is violating something. But of course, we do have experimental protocols who can even measure the quantum dimensionality of underlying systems. And so in that sense, I think of course machine learning will be able to do the same. I would train it and I would know the truth on all the test cases. And then I think that the machine learner will also be able to extract the features. Also because it can actually extract the same features as the trajectory. Because what does the neural network do? It takes the next data point in and then it updates a lot of parameters inside the network. What do I do in the trajectory theory? I take the data point in and I update my master equation, the density matrix. So in some sense, the most economical way for the network to work would actually to reconstruct the stochastic master equation. It doesn't know that there is such an equation and it uses 10,000 times as many parameters, but it actually effectively does that. So I think it can do everything that we can do.
Thank you very much.
If that is sad news, I'm sorry for that.
Thank you. One more question and then we go to...
Thank you very much for the nice talk. So I have just a small question about using neuronal network. So have you ever tried to use reservoir computing instead of neural networks?
No, so I have not. I mean, that's a super good idea. And I think that is definitely also inspiration for these kind of physical approaches down here. So I think that's a really good idea. But I have no experience with it.
And what's your opinion about that?
Well, I have a positive opinion about it. I think that this is you can say, when I say I've not experienced doing reservoir computing, it's because I didn't call it reservoir computing. But of course, I've been doing quantum dynamics with systems coupled to environmental degrees of freedom. And I can see the features coming out of that. And if the goal was to learn something, then I'm sure that, it's like putting ancillary degrees of freedom in some sense and see if you get a higher sensitivity. And framing it with the inspiration from reservoir computing is probably a really good idea. So I'm optimistic.
Let's thank the speaker again.